Hello students. So in the last lecture I could not cover up the fundamental theorems of integral calculus. So I'll do that today. So there are two fundamental theorems and there is no hard and fast rule which one is called first and which one is called the second. For example, in your textbook, that is Mathematical Analysis by Malik and Arora, the theorem that is stated first or the theorem that is referred to as first fundamental theorem is referred to as the second fundamental theorem in the real analysis by Bartel and Sherbert. So that's not a problem. The main thing is to know both the theorems. Okay. So as the textbook is Mathematical Analysis by Malik and Arora, so we will assume or we will take the notation or the terminology that is used in Malik and Arora. So let us have a look at those theorems. So these theorems give us a connection between the derivative and integral. Okay. So the first fundamental theorem, as per Malik and Arora, is if a function f is bounded and integrable on AB, then we may omit this word bounded because the definition of integrability itself that we have used means that f is bounded. Okay. So if f is bounded and integrable on AB, then the function f defined by fx equal to integration a to x ft dt, where a less than or equal to x less than or equal to b is continuous on AB. Okay. This function, when x is equal to a, this value of the function is taken as 0. Integration a to a ft dt is defined to be 0. Okay. Right. So this is a function of x, right? The upper limit is a variable, right? So this is a function of x, and this function is continuous. In fact, you will see it's uniformly continuous. Okay, on AB. Thus, further, if f is continuous at C belongs to AB, then f is also differentiable at C. Okay, and f dash C is same as f of C. Right. So this is the theorem. So let us see how to prove it. So we will use some concepts that we had done in the earlier lecture. Since f is bounded, so there exists a k greater than 0, such that mod of fx is less than or equal to k for every x in AB. Okay, that's easy. We start with any epsilon greater than 0 and let xy belongs to AB be any points. Okay, such that we suppose that x is less than y. And then we compute the difference fy minus fx. So what is fy? It is integration a to y ft dt, and fx is integration a to x ft dt. Okay. So we already have that theorem that we had done already. We can split the integral into two parts. So it's a to x and then x to y. Okay. So ultimately this the first and the last will get cancelled. So you will be left with integration a to x to y ft dt. And in the very previous lecture we had already done mod of integration is less than or equal to integration of the mod. Okay, so mod of this is less than or equal to mod of x to y ft dt, right? And so this is less than or equal to, but mod of ft is less than or equal to k. Okay, and we had also done that if f is less than g, then integration of f is less than integration of g. So here mod f is less than k, so integration over mod f will be less than or equal to integration over k. Okay, but k is a constant, it will come out, so k into y minus x. So ultimately we have seen that mod of fy minus fx or fx minus fy, same thing, is less than or equal to k into mod of x minus y. This is what we have proved. Okay, mod of fx minus fy for any xy inside this interval AB, mod of fx minus fy is less than or equal to k times of x minus y. And once this condition is satisfied, we have also already seen many times, this is the most preferred condition. If we can show that the fx minus fy is less than some constant times of mod of x minus y, our job is very much over. Okay. So this quantity we can make it less than epsilon whenever we choose mod of x minus y less than epsilon by k. So this will serve as our delta. Okay. So f is uniformly continuous on AB and hence continuous. Every uniformly continuous function is continuous. Okay. So why it is uniformly continuous? Because given any epsilon, there exists a delta, so this is the delta epsilon by k, such that whenever x and y their difference is less than delta, the difference between fx and fy is less than epsilon, so it's uniformly continuous, hence it is continuous. Okay, now the next part, suppose that f is continuous at c. So we have for h greater than 0, so we now need to show that f is differentiable. So we need to use that formula, f of c plus h. F is differentiable at c, so f of c plus h minus fc by h, that limit should exist. Okay, so this is the motive. Okay, so let us compute what is f of c plus h. So for the time being, we suppose h is greater than 0. So f of c plus h minus fc is a2c plus h ft dt minus a2c ft dt, and this can be written as c2c plus h ft dt, right? Okay, so this is integration c2c plus h ft dt. Okay, now let epsilon greater than 0 be given. Then since f is continuous at c, so there exists a delta greater than 0 such that mod of ft minus fc is less than epsilon whenever mod of t minus c is less than delta. Okay, so that means f of t lies between fc minus epsilon to fc plus epsilon whenever t minus c is less than delta. But mod of t minus c less than delta means what? T lies between c minus delta to c plus delta. Okay, so for positive this h, so for 0 less than, so if we take h lying between 0 and delta, then what can we say? We can say that from 2 we can say that fc minus epsilon is less than ft less than fc plus epsilon whenever c less than or equal to t less than or equal to c plus h. That means in the interval c to c plus h, f of t is greater than fc minus epsilon and less than fc plus epsilon. Okay, in the interval c to c plus h. So why we are looking for this interval? Because we want to estimate this integral. Okay, we want to estimate this integral c to c plus h ft dt. Okay, that is why we are looking what happens to the function inside the interval c to c plus h. Okay, so inside c to c plus h, the function lies between fc minus epsilon and fc plus epsilon. So you integrate, again we can use that result, f is less than g means integral of f is less than integral of g. Already we have done this. Okay, so integration of c to c plus h of this is less than integration c to c plus h of ft dt and less than this. Okay, so the first one is independent of t, so it will come out, and integration c to c plus h of dt is h. Okay, and this will be f of c plus h minus fc. Just we have already seen how. So we can divide both sides by h. H is positive, so this quantity is less than, lies between fc minus epsilon and fc plus epsilon. That means modulus of this minus fc is less than epsilon whenever 0 less than h less than delta. Okay, and this is nothing but the definition of right hand limit. Okay, right hand limit h tends to 0 plus of this quantity is fc. That means given any epsilon, the difference between these two can be made less than epsilon when 0 less than h less than delta. Okay, this is nothing but the definition of the right hand limit. Similarly, we can show by taking h negative, or by taking f of c minus h to c plus c, we can show that the left hand limit is also f of c. So the right hand limit and left hand limit are equal, and so this limit h tends to 0 of fc plus h minus fc by h is equal to f of c. And but what is this expression? This expression is nothing but f dash c. Okay, f dash c is equal to f of c. So this is the proof. Okay, and the second theorem, it states that let f from ab to r be a bounded and integrable function, and suppose that there exists a function f from ab to r such that f dash x equal to f of x for every x. Okay, that means the derivative of capital F is small f, right? Then integration a to b f dx is fb minus fa. Okay, this is something which we have been using since our higher secondary days. So the function capital F is called the antiderivative. Okay, so we use it, we find out the antiderivative of f and then put the upper limit and put the lower limit and then take their difference. Okay, this is something we have been already using since higher secondary. So and how it is justified, we will see it today. So the function f is called an antiderivative of f. Okay, so observe that it's an antiderivative because given function can have infinitely many antiderivative. They just differ by a constant. Okay. So since f is integrable on AB, so given any epsilon greater than 0, so we will use the Riemann sum approach here. It is easier in this case. For given any epsilon, there exists delta greater than 0 such that the Riemann sum minus a to b f dx is less than epsilon for every tagged partition of AB with norm p less than delta. Okay, where what is this Riemann sum? Riemann sum is summation of f of ti into xi minus 1. Okay, where ti belongs to this interval are the tags. Okay, their ti's are chosen randomly. Okay. So now for any partition P, so let us see what we can do. Now for any partition P equal to this of AB with norm P less than delta, we have f is continuous. Okay, so I missed one word here. We have okay. So I missed a word here. We have right. Okay, we have standard. Okay, put like this. Standard. There's some problem with stroke. Yeah, sorry. So we have f is continuous and differentiable in each subinterval xi minus 1 to xi. Okay, as it is so in AB, right? So f is continuous and it's differentiable. Why it's differentiable? Because f dash. Why it is continuous? Because already it's f dash. The derivative of f exists at each point. Okay, so differentiability implies continuity. So a capital F is continuous and differentiable in each subinterval. Okay, so whenever we have a continuous and differentiable function in a subinterval, we can always apply the Lagrange's mean value theorem. Okay, where you have already learned that Lagrange's mean value theorem in calculus. So by Lagrange's mean value theorem in the interval xi minus 1 to xi, there exists ti belongs to this such that, so in the original theorem there exists a c lying between a and b. Okay, so here we are considering for each subinterval, so there exists a ti inside this open interval xi minus 1 to xi such that, so if you remember, fb minus fa is b minus a into f dash c. Okay, that was the theorem. So it's f of xi minus f of xi minus 1 equal to f dash of ti into xi minus 1. Okay, so what is this? F of xi minus f of xi minus 1 is f dash of ti is nothing but f of ti by the given condition, right, into this. So we choose the above ti. So we have got some ti by Lagrange's theorem. We choose these ti's as tags of the partition P. Okay, then the Riemann sum, but we had already taken the partition with norm less than delta, right? And the tags we have selected using Lagrange's mean value theorem. Okay, so the Riemann sum as p dot f will become summation of this, and this is nothing but summation of this one, and so you can put a bracket here, better. Yeah. Okay, so so this is nothing but f of xn minus f of x naught, because all other in between the terms will get cancelled. And what is f of xn? It is fb minus fa. Okay, so ultimately I have got fb minus fa minus integration a to b f dx is less than epsilon, but epsilon is an arbitrary quantity, right? So we have made the difference between fb minus fa and integration a to b f dx less than any given arbitrary quantity epsilon. So we can say that this quantity is equal to 0. So fb minus fa is equal to integration a to b f dx. Okay, so this is the proof for the second fundamental theorem of integral calculus. Okay, so it's very important. Both the proofs are very important, so please go through this, and we will be left with some that is mean value theorems for integral calculus. I will do that in the very next lecture. probably after 2 or 3 days, maybe Monday. Okay, or sorry, Monday or Tuesday. Will probably we can complete our first 2 units. Okay, and then we can go to improper integrals. Okay, so please go through this. See you in the next video. Thank you.